I'm in my attic where I'm slowly setting up my electronics workbench for working on mainly audio equipment. And I literally just got this yesterday. It's a frequency function generator and an oscilloscope. So I got the frequency connected, square wave, 1 kilohertz range. So this should be a 2 kilohertz, I believe. Output is a 50 ohm right there. It's all built in, so I don't have to worry about that. And then this BMC cable kind of comes in here, comes out. There's a splitter for positive, negative, and then goes in into the other end, goes into the oscilloscope channel 1. So in effect, I'm not using the supplied probe, which looks a little bit different. The probes look like this, but it does the same thing. Because the positive and the negative, the ground, are here. So first I want to show you guys how a bad capacitor looks like. Bad capacitor, so when you feed a frequency like this, well, I'm doing it 2 kilohertz, so I can go up to 20 kilohertz. I'll show you guys a good capacitor. A good capacitor, well, you should see it like a dead short, meaning you shouldn't see much of a feedback from it. So if I connect a negative and a positive, these guys can see that the line is fairly flat. There isn't much happening here, just as we should expect. But if we connect this to a bad capacitor, this is kind of a challenge when I'm filming on my cell phone. We can try to do this. They don't touch each other. Now you can see this exponential kind of ESR effect. This capacitor is definitely dead. You can see it better here. There you go. Now, I've learned this. I don't want to sound like I'm kind of smart ass, because I'm just learning this, right? I've learned this from watching this video. There's a guy, channel's called W2AEW, not sure what that stands for, but he explains it here. See this curve here? Seeing the same curve. So let's watch what he's saying about it so we understand it.
Series resistance. So let's go look at a capacitor that I pulled out of an old monitor that actually failed. We'll see now with this bad capacitor in here, I've actually got to bring my volts per division back up again so I can actually see what's going on. So with this one, we can kind of see that effect that I mentioned earlier, where we have a step change due to the ESR, but then an exponential change due to the reduced capacitance. So this was a
exponential change due to the reduced capacitance. Now let's go when he was showing a good capacitor right here.
To take this 220 microfarad capacitor. Note that this is the indication here for where the negative lead is. So we'll connect the black mini grabber lead up to that, and then we'll take the other lead and hook it up to the other end, and watch what happens on the scope screen. So we've effectively, nearly completely squashed that signal. We're going to see the average value of it, and that's normal. We're also going to see a couple of little blips right at the edge transitions. And if we look carefully, if I turn the intensity up, we'll be able to see those little blips here and here and here. And that's normal. What we're looking at is the fact that we're not terminating this coax properly. There's a little bit of reflection coming back off of these leads.
Okay, so basically the signal should be squashed in a good capacitor. This is somewhat easier to work with because And indeed it is squashed. You can kind of see these little spikes here he's talking about. They don't come through my oscilloscope as good, but you can kind of see them. So I do see that squishness. Still kind of learning this. Yeah, there it is. Kind of see faint, but the signal has from the generator has definitely been squished. So anyway, this is a good capacitor. I love this method so much that I will now use these to test these for ESR. Anyway, that's all I want to show you guys.